Geometry, Unit 13, Section 1, Chords and Diameters. The first thing we need to do in this chapter and the next chapter, 13 and 14, are all about circles. We spent a lot of time talking about triangles this year, and then we spent some time talking about parallelograms, quadrilaterals. Well, now we're really diving into circles to finish off this year. And before we even get into that, we really need to talk about the different vocabulary we're going to see in circles, some of which you should know, and some of which is probably new to you. First of all, segments inside of circles have different names. PX, for example, what is PX? It goes from end to end of a circle and goes through the center of the circle, which we're labeling O. That's called the diameter. And that I am sure you are familiar with because we've talked about circles a little bit. We've talked about the area of a circle and the volume of a cylinder and so on. OY, that would be a radius. Now there's other radii in this circle, not just OY, OX, and PO. Those are all radii. There's only one diameter here, PX. But what would RW be called? RW is called a chord, CHORD. And it's basically a segment in a circle that does not go through the center. So it's like a diameter that it goes from two ends, it hits the circle in two spots. But a diameter goes through the center, a chord does not. I guess we could probably say that a diameter is a chord, a kind of thing like that, but a chord is not a diameter, kind of like a square is a rhombus, but you know, rhombus is not a square kind of thing. But a radius is different than those two because a radius does not go from two spots on the circle. It goes from the center to a location on the circle itself. And then what we have are special angles called central angles. And a central angle is basically an angle that has a, let me switch colors here. A central angle is an angle where the vertex is at the center of the circle. Vertex is at center of circle. Should probably have a the somewhere in there, but so like this angle right here, angle XOY or YOX, but we know the middle letter of an angle has to be the vertex angle. So that's a central angle because it's located at the center of the circle. So is POY or YOP. Even this angle here, POX is a straight angle because it's the diameter. That would be 180 degrees, right? These two would be less than 180. This one looks to be bigger than 90. This one looks to be a little less than 90, but together they are 180. All three of them together are 360. What is the degree arc measure of a complete circle? That is 360 degrees, and I'm sure you've known that for a while too, that the whole circle is 360 degrees. So we have angles in the circle, but then we also specify specific arcs, like this would be arc PR, arc RW, arc WX, arc XW, arc PW, so on. But how many different arcs could be labeled RW? So here is R, and here is W. And so when you think of arc RW, you probably think about, oh, hold on, there's a highlighter here. You probably think about this arc being RW, and that is true. But the truth is there's also another arc that could be called RW, and that would be this arc. Ooh, yes, this is getting kind of messy. That could technically be arc RW. Now, we wouldn't really refer to that as arc W. We would probably call it RPYXW. But the point is, there's sometimes referred to major and minor arcs. And basically, the minor arc is the smaller one, and the major is the larger. So, like this green arc here that I put, that would be minor arc, RW. And this whole thing then would be major arc, RW. Now, again, we wouldn't, let's pretend these other letters aren't there for a second. That's what major arc RW would be. Because they are there, it really wouldn't be called RW. It would be RP, YXW. But the point is, sometimes arcs can have two different names, and we'll specify them as major and minor and things like that. So in this case, I guess we could say the answer is 2. What is that, a crayon? Hold on, sorry. Yeah, it's a crayon. So there's 2. There could be a major arc RW, and really the way we should write arc RW, like for angle, we like to put an angle symbol in front of the angles. Well, for arc RW, we do RW with an arc over it. Different than RW with a line over it. That would be chord RW, would be line segment. There should be lines over these, right? Those are line segments, different than an arc. So there's major arc RW, and then there's also minor arc RW. Like I said, this is really not a great example because I don't think we'd call this major arc RW, but just wanted to get the point across that there could be two different arcs with the same name, and so we would specify the major and minor, of course, is the smaller of the two. Okay, here we have circle with a diameter AD, and we want to construct the perpendicular bisector of AD. So let's get our compass out. And you're not going to do a lot of constructions in these next two chapters. This is really just to kind of get a point across. The perpendicular bisector, we extend that beyond halfway and draw a complete half a circle arc, and do the same thing from the other end. And if you need to pause the video and catch up, please do. And then where they cross, I can use that as the 2 points to draw a line, which would be something like that. I got to move it over a little bit. About there. Okay. And then they tell us to label where the bisector intersects the circle XY. So that would be here. Call that one X. And here, Y. And label the center of the circle O. Well, because the perpendicular bisector is not only perpendicular, it is also a bisector. Bisecting AD, the middle of the diameter must be the center of the circle O. So you could always find the center of a circle by bisecting a diameter if you have a diameter. All right, determine and state all arc and angle measurements. All right, so let's talk about angle measurements. First of all, I see 4 angle measurements in here. We have angle AOX, and so angle AOX, and because it's a perpendicular bisector, we know this is 90 degrees. So angle AOX equals 90 degrees, and angle DOX equals 90 degrees as well, and angle AOY equals 90 degrees, and so does angle DOY equals 90 degrees. So we know that that's 90 degrees, that's 90 degrees, that's 90 degrees, and that's 90 degrees, and that's a consequence of the perpendicular bisector. Now, how about the arcs? I have a couple of arcs here. Now, this arc AX, I can refer to this as just AX. I don't have to call it minor AX, because major AX would involve these other letters, and technically I would call it A, Y, B, D, X if I wanted to go that way. So I'm just going to call this arc AX. I'll call this arc XD. This arc here I am going to refer to as DBY. Talk about that B in a minute, and also arc AY. So what can you tell me about these 4 arcs? Well, we mentioned earlier that the whole circle is 360 degrees. But what we just did was cut this into 4 equal pieces. So that would make each of these 90 degrees, just like these angles are 90 degrees. So arc AX is 90 degrees. Arc XD is 90 degrees. Arc DBY is 90 degrees, and arc AY, or YA, either way, is 90 degrees. And I know that because the 360 circle was divided into 4 equal pieces. 360 divided by 4 is 90. But we also have some other arcs too, right? I mean, we could combine some of these. We could say arc, how about AXD? What's arc AXD? And so that's arc AXD. That's combining these 2 arcs together. And I see that that has to be 180 degrees for 2 reasons. One, arc AXD, and I'll highlight it for a second, you don't have to. Arc AXD is a combination of 2 arcs we already said were 90. And they had to be 90 because it cut, the 360 into 4 equal spots. So that was 90, 90, total of 180. But also we started off by saying that AD is a diameter. What does a diameter do? It cuts a circle in half. And half of a circle, half of 360 is 180. So diameters are really your friends here when you're working with circles. These next 2 chapters, always look for diameters because they They cut your circle in half. They cut your 360 in half to 180, and there's a lot of important stuff that we could get from having a diameter. So there's other arcs here, but the point across we're trying to get is that these central angles are 90, and then each of these individual arcs have to also be 90, because just as all the points meet at angles that add to 360, cut those up into 4 equal parts of 90s. Well, my circle is 360 degrees of arc, and we cut that into 4 equal pieces. So this is 90 degrees, 90 degrees, 90 degrees, and 90 degrees. So then we get what's called the central angle rule. I'm sorry, I messed up. This information should also be up here. I never answered choice C. I was still answering part B here. But let me answer this real quick, and I'll go back to part C. The degree measure of a central angle is blank to the measure of its intercepted arc. The concept that this construction was attempting to go through before I goofed up over here was that a central angle, if I pick one of these angles and highlight it, let's say DOX, or X over XOD. We determined that this was 90 degrees, and we also determined that the arc was 90 degrees. So what do you think the relationship between a central angle and the arc it intercepts is? The answer is equal. That a central angle equals the measurement of the arc. So if I know an arc measure, I can determine a central angle measure, and vice versa. They are equivalent. And here's the same thing just said backwards. The degree measure of an arc is equal to the measure of its central angle. So that's a nice, easy relationship here. All right, but let me go back to this question here. Angle ABD. What's angle ABD? We don't even have that angle drawn, so let's actually draw it. So I'm going to draw a line here. I'm going to use a different color to really emphasize this angle. Angle ABD. What do you think that angle is? Well, to answer that, I think we have to first answer the question of what do you think the measure of angle AXD is? What is angle AXD? Angle AXD is right here. Here to here. What do you think that angle measurement is? And I see that, well, this was 90 degrees. And this is a radius, this is a radius. And radii are all equal length, which makes this little triangle in here isosceles. So this has to be 45 and this has to be 45. And I actually get the same thing over here. This has to be 45 and this has to be 45. So this whole thing has to be 90 degrees. And how is that helpful for me to get this angle? How is this angle helpful to get this angle? And the key is, I know the picture's getting sloppy and the video is getting long here. Just stay with me for one more second. Is that this angle opens up to how much arc? Oh, it opens up to this much arc. And that's 180 degrees of arc. And this angle opens up to how much arc? Oh, it opens up to this much arc. Also 180 degrees of arc. If angles open up to the same amount of arc, then they themselves must be equal. Now, this is not called a central angle because it's not at the center. It's what we call an inscribed angle. We're going to learn more about that another day. And basically, it's half the amount of arc it intercepts as opposed to equal like central. The answer here is 90 degrees. And that kind of looks like 190. Let me change that. The reasoning is because basically, if you have an angle on the circle that connects the endpoints of a diameter, it's always going to equal 90 degrees because they're all going to open up to the same amount of arc as this angle does here. And we'll talk more about that another day. We'll talk more about inscribed angles, but basically, no matter where you draw an angle, if its endpoints go from one end of a diameter to anywhere on a circle to another endpoint of a diameter, it's going to be 90 degrees because it's opening up to 180 degrees of circle arc, and it's an inscribed angle. We'll talk more about that again. All right, sorry for the long video. The intro videos tend to do that. See you later.